Hello everyone. Welcome to the fifth lecture on the topic of open channel flow. In this lecture, we will continue our discussion on the topic of energy depth relationships in open channel flows. Now, in this lecture, we will particularly focus on the calculation of critical depth for open channels of different shapes. As you know that we have already discussed uh, in the first lecture on the energy depth relationships, the basic aspects of it, and we are now pretty clear about what is a critical flow, a subcritical flow, and a supercritical flow, how they are categorized, and we have extensively discussed on what is a specific energy diagram. And the concept of specific energy, as we discussed that many a times, that it's very important in throughout the course of this open channel flow. So in this lecture, we're going to apply our previous knowledge, our built-up knowledge on the energy depth relationships and the concepts of specific energy and critical depth for the calculation of critical depth for open channels of different shapes. We will start our discussion on the very basic rectangular shaped open channels, or the open channels with rectangular cross sections, and try to estimate or calculate the critical depth for it. So we can see the rectangular section at the top, and for the rectangular section, the top width, capital T, is equal to the breadth of it is equal to capital B, and the flow depth, let's call it small y. So the flow cross section, the cross section of flow here is given by capital A is equal to B into y, and of course the top width is given by the breadth of the channel is equal to B, which is a constant for rectangular channels. So we are going to, of course, invoke the mathematical expression for the critical condition, which was derived and discussed extensively in the last lecture. And so we are going to invoke that, which is given by q square into capital TC by g into capital AC cube is equal to 1. And using the above relationship for a rectangular channel, it can be easily derived that the critical depth of flow for a rectangular channel can be given as YC is equal to small q square by g to the power 1/3. This equation has been highlighted in blue in the slide. Note that the small q is the discharge per unit width of the channel, or small q is equal to capital Q by capital B. So this is the discharge intensity. Also, I want to point out something, that this lecture and in upcoming lectures, many derivations will be done. So to show all the derivations on the slides is not particularly possible. So I really urge you to do the derivations yourself while looking at the slides. So we have calculated the critical depth, the expression of critical depth for a rectangular section. So we again invoke the relation of the mathematical expression for critical conditions, q square into TC by g capital A cube is equal to 1, which again equals to VC square by GYC. I want you to look at the first equation on this slide. And so it can be very easily seen that capital VC square by 2g is equal to yc by 2, or the velocity head of the flow is equal to the critical depth by 2, or half of the critical depth, where capital V is the mean velocity of the over the cross section of the flow. So for a rectangular section here, the specific energy at critical depth can be given as capital E subscripted by C is equal to yc plus vc square by 2g is equal to 1.5 into yc. So here we can see that the specific energy equals to 1.5 times the critical depth for a rectangular cross section. So this is an important result, and this basic results I urge you to remember or by heart. The Froude number, what we have already discussed about Froude number. The Froude number is given by, is a non-dimensional number given by Fr is equal to capital V by root under G into capital D, where we discussed that capital D is the hydraulic depth, which is used as the characteristic length for open channels. And so for a rectangular cross section, the hydraulic depth, by definition, the hydraulic depth is given by the ratio of the flow cross section by the top width of the channel, or D is equal to A by T. And for a rectangular channel, that equals to the flow depth only, or small y. And hence the Froude number here is given as Fr is equal to V by root under Gy. This is the classical expression of Froude number for a rectangular channel. V is Froude number equals to capital V by root under G into Y. Now from the rectangular channel, let's move on to another channel of another cross section, and we let's discuss on open channels of triangular cross sections. So we can see open channel with a triangular cross section on the right. We can see the diagram of it, and so here note that the side slope of the triangular cross section is given by m:1, or the side slope is given by m horizontal is to 1 vertical. This is the way by which we designate the side slopes of the cross sections, m:1. And so in that case, if the side slope is m:1, the cross sectional area here is given as capital A is equal to small m into small y square, and the top width is given as capital T is equal to 2my. So again, what we are going to do is that we are going to invoke the classical expression for the critical condition for flow in open channels, and we can write I want you to focus on the second on the equation at the center of the slide. Capital Q square by G is equal to capital A C cube by TC, and by substituting the values of AC and TC from the previous expressions, we can derive that Q square by G is equal to small m square into yc to the power 5 by 2. So for an open channel with a triangular cross section, the critical depth is given as by the equation highlighted in blue, which is the last equation of the slide, and is given as yc is equal to under bracket 2q square by gm square raised to the power 1/5. The specific energy at critical depth here for a triangular cross-section channel is given as EC is equal to YC plus VC square by 2G, and by substituting the values of Q square and AC square from the previous slide, we can easily derive that the specific energy at critical depth, or EC, equals to 1.25 times the critical depth. So remember that the specific energy at critical depth for the rectangular channel was 1.5 times the critical depth. Here the specific energy is 1.25 times the critical depth. Note also that the critical condition, or the critical energy, the critical specific energy at critical condition is independent of the side slope here. There is no small m in the expression of the specific energy at critical condition, or EC, so it's independent of the side slope. The Froude number here is given by Fr is equal to V by root under G into capital D, and here D is equal to A by T is equal to small y by 2. So the Froude number is given as V into root 2 by root under GY. So here also note that the Froude number for the rectangular shaped rectangular shaped channel was V by root under GY. Now, having discussed about the calculation of critical depth for rectangular and triangular channels, now we move on to calculation of the critical depth for trapezoidal channels. So here also we assume that the side slope of the channel is given by m:1, and the base width here is capital B. So the cross section area is given as A is equal to y into under bracket capital B plus my, and the top width capital T is given by capital T is equals to capital B plus 2my. And so invoking the mathematical expression again for the critical condition, we can write capital Q square by G is equal to capital AC square by AC cube by capital TC, which equals to under bracket B plus myc cube into yc cube by B plus 2myc. So this is the expression for estimating the critical depth for the trapezoidal channel. See, unlike the channels with triangular or rectangular cross section, here the estimation of critical depth is not straightforward, it's a little tricky. So the equation which is given here is an implicit one, and it doesn't give an explicit expression for the calculation of the critical depth like the previous ones. However, we can use another technique which is for estimation of the critical depth, which is the technique of non-dimensionalization of the above equation and using charts and plots to arrive at a possible solution. So the right hand side of the equation in on the previous slide can be written as can be simplified as this: capital B to the power 5 by m cube into 1 plus xi cube into xi cube, and by 1 plus 2 xi, where xi is equal to small m into yc by capital B. So setting this in the previous equation, we get the expression of expression which is given and which is highlighted in blue. And this is the equation which is highlighted in blue is the equation we are going to use in estimating the critical depth for trapezoidal channels. So we are going to use a table in which the values of psi is given against values of xi, and using the table we are going to derive the critical depth for trapezoidal channels. The table is shown in the next slide. Here are some typical values which gives the values of value of psi against values of xi, and using this values we can easily calculate the critical depth using the expression which was highlighted in blue in the previous slide. Now, again invoking the classical relation mathematical expression for critical condition given by capital Q squared by G is equal to AQ by T, and substituting the values of the values of the cross section and the top width from the previous slides, we can arrive at the first equation of the slide. Q squared by G is equal to capital B plus myc whole cube into yc cube by capital B plus 2myc. So this we have to substitute now in the expression of the specific energies at critical depth, which is the second equation of the slide. And by substituting the value of Q square from the first expression into the second equation or second expression, we can write the third equation of the slide, which is given by capital EC is equal to YC by 2 3 plus 5 xi c by 1 plus 2 xi c, where xi is equal to, of course, m into yc by capital B. So this is the expression of specific energy at critical depth for a channel of trapezoidal cross section. Again, I will definitely urge you to do the derivations yourself so that the whole concept of these derivations becomes clear to you. The Froude number for the trapezoidal channel can be written as Fr is equal to capital V by root under G into capital A by capital T, and as capital A by capital T equals to B, we substitute the values of the cross section and the top width from the previous slides, and we can see that the Froude number is an expression of is a function of my by capital B for a given discharge Q. So that's all for this lecture, and we will continue the lecture on the energy depth relationships, and we'll conclude the topic of energy depth relationship in the coming lecture, in the next lecture. Thank you very much.